Hello and welcome to the public webinar session on testing T1-based services and business voice services. We'll be covering testing applications using a variety of JDSU test sets, including the T-BERT 5800, T-BERT 6000A, T-BERT 8000, and HST-3000. Today's sessions will be recorded, so recordings will be made available to you and anyone who registered for the session and didn't attend because of other urgent matters. You're welcome to forward links to the session onto your coworkers as well if you think they'd benefit from this. We will offer these sessions periodically. Every month or so, we try to offer at minimum a session on Ethernet testing basics and then one other specialized session, such as this one on T1-based services and business voice services. A few other logistics I'd like to cover before we get started here. All lines are muted, so if you need to communicate with me, you can do it via the WebEx by using the Q&A panel or the chat panel. I will be monitoring them periodically, and we'll answer your questions. There'll be break periods between different sections in the presentation at which I will answer your questions. Again, the session is being recorded, and we'll pause periodically for breaks. The agenda for today, we're going to start off with a brief overview of JDSU's T1 and business voice testing portfolio. So I'll give you a description of the key products that are used to test the services we're going to describe today. We're going to cover some technology basics on T1, talk about bit error rate testing and also testing T1 MPLS service. And then for the second half of the session, we'll talk about business voice services, including ISDN PRI and voice over IP, and in particular for voice over IP, how to test SIP trunks. So the key products today, again, are going to be the HST-3000, the T-BERT 5800, the 6000A, and the 8000. I'm a member of a team at JDSU called the SSO, or Sales Support Organization, and I'm a technical specialist on these products, which are what we refer to as our Metro portfolio. JDSU has a wide depth of products. The division I work for, Network Service Enablement, focuses on test equipment, but we make SFPs and optical components and a wide variety of other equipment too. Today, at my disposal for this training, I do have an HST-3000 as well as a T-BERT 5800 and a 6000A. So if you have any of these test sets, you can try to push the buttons and follow along as we go. The other products that I support include the 8000, which is basically a larger version of the T-BERT. It shares the same graphical user interface, has a few extra capabilities. And then also, we've recently just announced a product called JMEP. It's not as relevant to the stuff we're going to be discussing today. We'll be focusing on T1 and voice services today. But for Metro Ethernet, we now have a product that, in the form factor of an SFP, that can be your loopback device for testing. We're going to be doing a second session this month. I believe it's next Monday. And the same invitation that you answered to attend this session will allow you to participate in that as well. And there will be more information forthcoming there on the applications. But it's kind of exciting. We have a loopback device now that's in an SFP. So you could put this in a switch, and then you don't need a second HST-3000 or T-BERT in order to do loopback testing for Metro Ethernet. That's the only product in the list here that is Metro E only. The HST as well as the other T-BERTs all do T1 testing that we're going to discuss today, as well as voice over IP. The HST-3000 is at the low end of the offerings for this. It's a modular test set with swappable modules to go from Ethernet to T1 to DSL and copper testing. And yeah, it covers most of the applications we're going to cover today. T1 and DS3 BERT. It can do frame relay, which we're not going to cover today. It's more of a legacy application that's not covered in the T-BERDs. And also does ISDN PRI. The main limitations are on Ethernet. It's just a single port unit, and it's limited to GigE. That's not upgradable. Support 10 GigE. Supports IP video and voice over IP too, but it doesn't do SONET. It doesn't do fiber channel and some of the advanced capabilities, higher speed capabilities that are offered in the T-BERDs. When you move up to a T-BERD 5800, which many of you may have, you still get your basic T1, DS3, and gigabit Ethernet testing capabilities, but you also get 10 gig. It's a SONET all the way up to OC192 or 10 gig Ethernet. It's also can be configured as a dual port platform where you can run two simultaneous tests, either two GigE tests or you could be birding a T1 and testing a GigE at the same time, or GigE and 10 GigE, so it does two simultaneous tests, the sort of two HSTs in one. Still does voice over IP as well, so all the applications we're going to cover today are covered in the 5800. The 6000A is a slightly larger form factor T-BERD, which includes all the capabilities of the 5800, but it can be dual 10 gig instead of single 10 gig. And it's also a modular platform that can also be an OTDR or a dispersion test set for fiber or an optical spectrum analyzer. So it's a more versatile modular test set. Then when you move up to the T-BERD 8000, you can get 40 gig and 100 gig capabilities. So again, it's a larger form factor. Still portable, but it's something you want to probably put on a cart and roll around as opposed to just carrying around in your hand. So all of these are capable of the majority of what I'm going to cover today. I will show the differences as we go along. And I do have VNC sessions into each of these as well. So there's my T-BERD 6000. Right now it's set up for an Ethernet test, but I'm going to change that to another test mode when the time comes. I also have a session into a HST-3000. So here's my HST-3000. It's currently set up for a T1 test. So we'll see that, go through some testing examples of that. I also have a VNC session into a T-BERD 5800. It's currently set up for a T1 test as well. Already mentioned the JMEP, the companion. Again, a brand new product. We're going to start shipping in January. We're currently taking offers, but or currently taking orders for it. But for Ethernet testing, it's a loopback device in an SFP, so it could be inserted into an Ethernet switch or a NID or other device in order to give you a loopback for Ethernet. So if you have interest in that, I encourage you to contact your account managers. The HST-3000, which we will focus on today, its basic architecture is outlined in this slide. The HST-3000 is modular, so there's several different modules which we refer to as SIMs, subscriber interface modules, that can be inserted or installed on the back of the HST-3000. The module that we're going to focus on today primarily is the T1 module. It actually comes in three different form factors. It could be T1 only, which is pictured here, or it could be a T1 module combined with DS3 or even combined with copper testing capabilities. But we'll go over some of the T1 capabilities of that today. There's, again, different modules for different test applications as well. A quarter turn of a screw on the back of the module lets you remove it and then put another one in its place. The top of the HST-3000 has all the management connections. Most important, there's an Ethernet connector, which serves two primary functions. I'm using it to remote into the unit right now. So I had it pull an IP address off of my my home router, and I'm connected up to it, and via VNC I have a session into it. So I just showed you the screen snapshot, but I'm doing that via its management port. Next to the management port, there's a USB connector, which could be used to put a thumb drive on to copy your test results to. You can put a keyboard on it if you wish to make it easier for text and alphanumeric entry. You can also put a fiber optic microscope in it if you're handling optical cables. So there's a number of uses for that. But the most common is to put a thumb drive in to copy your test results off to. There's also a headset jack to the next to the USB connector that you can use to talk and listen when you're doing business voice calls, be it ISDN PRI or a SIP trunk. It's not necessary to use a headset, but you can cut down on some of the background noise by doing that if you're in a very noisy environment. The base of the unit has a speaker, and the front of the unit has a microphone. So you can use this speaker and microphone to talk and listen as well. It's a speakerphone. You don't have to hold it up to your head like a butt set, basically at arm's length. You can use this just like a speakerphone and talk and listen using the built-in capabilities for voice. The rest of the front panel is your user interface. The top of the unit has some status LEDs. The first one is labeled sync, and typically when you plug into a circuit, you're looking for a green LED there to indicate that you've connected to the line under test OK. So you have a link to the device that you've plugged into. There's a data LED that indicates you're receiving traffic on that link. There's an error LED, which will illuminate red if you take any errors. There's an alarm LED. We're going to talk about different alarms on T1 in a little bit, but the T1 goes into alarm. That alarm LED is going to light. There's a loopback LED. If the HST is put in loopback mode in order to run a bit error rate test to it or for Ethernet testing, that loopback light will illuminate. Finally, there's a battery indication LED. Below the LEDs is your LCD panel, and that's where you see all your test results and see all your configuration options and menu options in order to get the HST-3000 into the mode you want it to. When you're choosing from options, they're typically numbered, so you can either use the up and down arrow keys to move to an option that you want, or you can even hit the number associated with the option using the keypad. At the base of the LCD screen are 4 labels. In this case, this is an example of a screen for Ethernet measurements, and they're labeled Ethernet electrical, Ethernet optical, Ethernet TE, etc. But to choose one of these test functions, you tap the soft key below it. So these 4 keys correspond to these 4 labels at the base of the LCD panel. Below the soft keys are a cancel key and an OK key that are used to select an option or to cancel out of it. So if I wanted to do a terminate test at this point, I would hit OK. If I wanted to then come back to the screen and choose a different test, I would hit cancel. So cancel always backs you up to the prior screen or board's input if you're starting to type something in and you change your mind. We talked about the arrow keys a little bit already, but it moves you around within a screen, either up and down among the options, or it can also move you from soft key to soft key too. So I could hit the right arrow key to move over to the Ethernet optical soft key. In some cases, there's more than 4 functions, and there's only 4 soft keys. So in that case, there's always a little arrow pointing to the right of the last soft key, and you can, from the last soft key, hit the right arrow key to relabel these keys in that case. Below the arrow keys are 4 navigation keys labeled Configure, Home, Auto Test, and System. The Configure key puts you into the configuration menus where you can set up a test. So for T1 testing, for instance, you need to specify whether you're going to be clocked internally or externally. You need to be able to specify your line code and your framing, so your ESS and B8ZS, for instance. So we'll talk about some of these options, but to set all that stuff up, you hit the Configure key after you launch your test. Once everything's configured, you want to get back to the main screen where you can do your test selections and see your test results. You hit the second soft key, which is labeled Home. That's where your results are. Auto test, we're not going to cover today. There are some canned tests available for T1s that are under there, but we'll focus today just on the manual testing capabilities that you configure, and then you see the results for under the first two soft keys. Finally, the last soft key is labeled System, and that's where you do things like set the date and time on the HST-3000, set up the IP address for the management port. I had to do that before we got started here. And do software updates, do file management by copying files around. All of that's under the System key. Below that's a keypad, so you can do your alphanumeric entry from the pad. The alpha is a little more difficult than on the T-BERDs where you have a full screen, but you can think of it as being similar to texting from a flip phone where you didn't have a full QWERTY keypad. There's a second function associated with the keypad, and a few of the keys are labeled with the second function, but you can adjust volume, screen brightness, and screen contrast by using the second function key in conjunction with one of the other buttons. Finally, there's a power key. So that's the HST-3000. Let me give you a quick view of a couple of the capabilities of it. Let me just set it here at the top of the unit. And right now, notice my screen is labeled Home, T1 BERT. So I'm in the Home menus. But if I hit the first soft key, I'm going to have to do that by hitting the corresponding function key, F5. When you remote it into it, does configure. Basically, it's laid out F1, F2, F3, and F4 for the soft keys, F5 through F8 for the navigation keys. So F5 will bring me into the system screen. I'm sorry, F8 will bring me into the system screen. F5 brought me into configure. And I set up remote operation already. That's the screen I'm in now. If I hit the cancel key and back up one menu, now I can see my instrument setup options. Under ports is where I set up my Ethernet port, and it pulled an IP address of 192.168.0.16 from my router, and that's what I use to VNC into it. If I hit the cancel key and back up, I could go back to my tools menu, and I have a file manager. I can see what options I have loaded on my unit. For what we're doing today, you need the ISDN PRI option, and you need voice over IP options. Particularly, you need the voice over IP options for SIP call control. But in here I can see all my options. You also need voice over IP. So that's the system menu. I can restore factory settings in here also, which is a useful function, especially if you're sharing a meter with other people. You may periodically want to restore it back to defaults to get to a known state. It won't wipe out the hard drive. So if you save configurations or save test results, they're still going to be there, but just the current configuration of the unit is set back to a default. And typically, when most of the testing that we're going to describe today, most of the settings you do leave as defaults. There's just a handful that you change. So it's always good to have a known state to start from and only make the changes you need when you're running a test. So those are some of the key things under the setup menu. And today we'll be focusing on capabilities from the T1 SIM as well as from the mainframe itself. You use the management port on the mainframe for voice over IP testing. The ports that we're going to plug into for testing are on the side of the HST-3000, and they're your T1 ports. There's actually two sets of ports on the side of it, and they're labeled transmit and receive, and port 1 and port 2. Port 1 is the port that you use for testing. So port 2 is used for pass-through mode. The HST-3000 can monitor a T1 as well as terminate it, but if you're terminating a T1 in order to place calls, you use the top set of jacks that's labeled PRI, and or if you wanted to BERT out a T1, again, you use the top set of jacks. For monitoring, you use both pairs. You use the receive on the top and the receive on the bottom, and that way you can monitor bidirectional traffic on a T1. But in most cases, if you're terminating the circuit to either BERT it or to place PRI calls, you just use the pair of jacks labeled PRI, primary. We've already looked at the interface, but we can look a little bit closer here. At the top of the interface is a navigation line, which just tells you what menu you're in. In this case, Home T1. Below that is Quick Help. They're saying press a number to use, or the arrow keys. Then you get your menu item and descriptions, and then the soft keys at the bottom. Okay, moving on to the T-BERT 5800. Architecture of it is outlined here. The top of the unit has connectors for T1 as well as Ethernet, as well as DS3, and for that matter, SONET, and optical and electrical Ethernet. So you can move from one test to another without swapping modules or without swapping SIMs like you have to on the HST-3000. So it's non-modular. The only modularity is in the SFPs and XFP ports themselves. For Ethernet testing or SONET testing or fiber channel, you can put different SFPs in to test different wavelengths or different varieties of optical Ethernet or SONET. There could be 850 nanometer for single mode, multi-mode fiber, or 1310 or 1550 for for single mode fiber, and you could accommodate all of them by just swapping an SFP or an XFP. For that matter, some of the less common Ethernet physical layers, PHYs like 1000 base BX or 100 base SX, all those things you can get by just putting different SIMs or different SFPs and XFPs in. But that's the only modularity. To go from T1 to copper Ethernet or to a given SFP, you don't need to swap modules. You just choose it in software. The front of the unit's all screen, no buttons to push physically. You just point and click to do everything. And then the side of the unit has your management connections. There's 2 USB ports, which you can hook up a thumb drive or a mouse or a keyboard or a fiber optic microscope or power meter. So a number of accessories you can put on there. And then next to that is your Ethernet management port. There's also an RS-232 port used for VT100 emulation if you need to go into a craft port or into the console port on a router in order to configure it. You can run VT100 emulation on the T-BERT and use it similar to how you might have used HyperTerm in the past on your laptops. So that's the basic architecture of the T-BERT 5800. Do want to point out something about the T-BERT 5800s. We do have a special in place now where we can do quick ships for the holidays. So if you maybe you're currently an HST user, you like what you see in the 5800. We do have a number of packages available that we can still ship by end of year. So if there's end of year funding available, again, I encourage you to contact your account managers or send me an email. And I'll get it to the right person, and we can still ship at the in time for end of year if you have budget you need to use. The GUI of the 5800 is outlined here. So across the top, for starters, you can choose between a test menu and a system menu. The system menu is like the system menu on the HST-3000 in that you can do your file management, you can do software updates, you can set it up for remote operation. And then the test menu is where you see all your test results. You can think of that like the home key on the HST-3000. The menu bar below that lets you select the test you want to run, whether it's an Ethernet test or a T1 test. Lets you change your view from the default layout. You can generate reports. There's a tools menu that lets you do things like reset the test to defaults or view the options that are installed on your unit. And then there's online help, which is your user's guide. Below that, it shows you the test you're running and a message bar, which gives you the status of loopbacks and some other information when you're testing. Then you get a quick config. So any commonly changed settings you can change right on the main screen here without having to go into the setup key. But detailed configuration you can also always change in the setup button. Below that you have an LED panel plus 2 sets of results. So you can concurrently see the status of your connection and then any 2 user selectable results. The results you see in these 2 screens are dependent upon the result group and the result category, both of which have drop-down menus which you can click on to see different types of results. And we'll walk through some different results categories and groups as we go through some testing applications. Then at the base of the unit is your actions panel. That's where you loop devices up and start and stop traffic. Finally, to the right side of the unit are soft keys, which are different for different test applications. Actually, what's shown here is an Ethernet screen. So some of the automated Ethernet tests and toolkits are shown here. When we do T1 testing and voice over IP testing, we'll see a different set of keys here. But the setup key is the most commonly used one, which brings you into a screen to do your detailed test configurations. If you're using T-BERT 6000As, or if that's your product of interest, the architecture is shown here. The GUI, the screen, is pretty much the same as the T-BERT 5800, but the hardware is laid out a little bit differently. The top of the unit has your USB ports and your Ethernet connector for management, but you can also put optical test functionality into ports in the top of the unit. So you can put a power meter or optical return loss or visible fault locators into the unit in the slots at the top. The side of the unit is an extractable module, which could be an OTDR, it could be an optical spectrum analyzer, an optical dispersion module, or, as we're going to discuss today, it could be a module called the MSAM, which stands for Multiple Services Application Module, but that does your Ethernet and T1 testing, as well as Datacom, DS3, and Sonnet. The MSAM is pictured here to the right, and as you can see, it has 2 sub-modules that plug into it. We refer to those sub-modules as PIMs, or physical interface modules. And to do what we're covering today, you would need a T1 module, a T1 PIM, in order to do the T1 testing and PRI, and you would need an SFP PIM, or an SFP plus PIM, which is pictured here, in order to put an SFP into for voice. It could be a copper SFP with an RJ45 connector or an optical SFP with an LC connector. If it's optical, it could be for single mode or multi-mode fiber at a variety of wavelengths. The T-BERT 8000 is the next step up in our T-BERT product line, and it actually for T1 and business voice testing uses the exact same module as the T-BERT 6000A. But instead of just being able to hold a single module in the side of the unit, you put dual module carriers into it. And in one slice or one dual module carrier, you could actually put 2 different MSAMs. Or for that matter, you could put an MSAM and an optical spectrum analyzer, or an MSAM and an OTDR. So you can put multiple modules into it to do different types of tests. There's also a special module for 40 and 100 gig Ethernet testing. So the latest technologies before they get can move into smaller form factors are going to be supported in your T-BERT 8000 first. It's stackable, so you can concurrently have modules in it for low-speed Ethernet testing in 100 gig or T1, and you can mix and match and run concurrent tests on all the different modules as well. The GUI for the 6000 and the 8000 is almost identical to the 5800. The only difference is that they have buttons on the front panel to switch between the system and the results, whereas you do that on the 5800 by tapping the system and the test key at the top. There's no buttons on the 5800. But once you get into the test menu, the GUI is the same. Let me bring up my 5800 now. We'll take a quick look at that. The system menu. Right now, in the menu where I set up my network settings, and I gave it an IP address, and I'm using that address to VNC into it. If I back up to the main system menu, you can see I can do things like software updates. Look at my files that I've saved, all the reports, for instance, set date and time, format a USB stick. So all my management functions are in here. Software updates are very simple to keep your unit current. You go into Upgrade, you go to the Network tab, and it should default to a server address of 5800.updatemyunit.net. As long as you're on an internet connection, at that point you can connect. And it'll go to that JDSU managed website and let you know what the latest software revision is and allow you to download it. We just released version 5.0 on the T-BERT 5800, so it's been posted for less than a month. Actually, I think it was released by engineering a couple weeks ago. I think it's only been posted for about a week. But I do encourage you to go and update your units if you are doing 5800s. And get this version 5.0. The test menu, we're going to go through plenty of examples of testing on that, but we're always going to start out in the Select Test menu, choose a test to run, set up the test either under Setup or Quick Config, control the test in the Actions panel, and view results. Likewise on the T-BERT 6000A. We have our main results. I have to hit a hard key in order to switch over to the system menu, but the results screen is going to look the same. So we'll come back to that later. The Select Test menu, as I just dropped down here, we're going to spend most of our time today in the DS1 options in there, but the DS1 selection, and it lets you do BERT, it lets you do ping and monitoring if you have PPP traffic on the T1, so it is not limited to just layer 1 BERT testing. You can do IP level testing as well, and if it's being used for a voice trunk, it can do PRI emulation as well as CAS emulation. The older T1 trunking protocols are supported. For Ethernet, it can do copper testing or fiber testing, can do voice over IP, and those are going to be our main functions today. But the T-BERTs also do E1 testing, SONET, SDH testing, fiber channel, as well as CIPRI. And for wireless providers, there's some special test interfaces to test the wireless front haul networks too. At this point, I'm going to move into T1 testing applications, but I do want to entertain questions real quick to see if anybody has questions about the different platforms. I do have a question about VT100 emulation. If a conversion cable is needed for DB9 to RJ45 to use the craft interface, and answer to that is yes, you do. We do. If you get the VT100 option on the T-BERTs of the HST-3000, it will come with the cable to go to DB9, and then you need to adapt that down to RJ to an RJ48. Any other questions before we move on? Okay, well, let's move on to T1 testing. The main T1 testing applications are outlined here. You can do both in-service monitoring and out-service testing. In-service monitoring would be plugging into monitor ports or bridging a T1 and looking at live traffic being transmitted across the T1 between two devices. So when you're doing that, you can do frequency measurement, look at alarms and do error monitoring, measure a variety of statistics. You can listen to audio. And with the T-BERD, you can also do capture decode if there's data going across the T1. If it's voice, you can listen to the voice. If it's data, and it's encapsulated using PPP protocol, you can capture it and decode it. For out-of-service testing is when you're plugging in as an end device and you're terminating the T1. And in that case, you can do bit error rate testing. It can be done to a loopback device or head-to-head between two test sets. You can measure round-trip delay. There's a special BERT pattern for delay measurements. You can do PRI emulation. For that matter, you can do CAS emulation and some other older T1 trunking protocols too. And again, if it's HDLC PPP data, you can transmit IP traffic on that and ping devices to verify connectivity. We're going to focus on these out-of-service testing capabilities today. But the in-service monitoring is pretty simple to set up. I'll show you the setup options for that as well. Test sets that are optioned for T1 testing should come with the cables you need. All units pretty much ship with Bantam to Bantam cables. Some of our packages may have the Bantam to RJ48Cs and some may not. Sometimes you get Bantam to RJ to alligator clips and some other cables as well if you get a full DS1 table kit. But these are the two most common cables used for T1 testing. The side of the meters themselves, be it an HST or a T-BERT 5800, is going to have Bantam jacks on it. So the connector here, which has tip and ring, basically to carry the T1 signal, can either connect through to another Bantam or to another interface. If you're plugging into a device with an RJ48C connector or an 8-pin modular jack, you need an adapter cable, and that's what's pictured here. So there's two Bantams that go into the T-BERD. So if it's Bantam to Bantam, you need a pair of these. The Bantam to RJ48 cable goes dual Bantam on one side to the RJ48C on the other. The RJ48C looks just like an Ethernet connector. It's an 8-pin modular jack, just like Ethernet, but it is pinned out differently. The standard pinouts for the color code will typically be the same. It'll follow the same EIA standard and go orange stripe orange, green stripe blue, blue stripe green, brown stripe brown, but the functions of the pins are different. On Ethernet pins, 1, 2, 3, and 6 are used to transmit and receive, at least on 100 meg Ethernet. On gigabit Ethernet, it uses all 8 pins. But for Ethernet at lower rates, it was 1, 2, 3, and 6 for transmit and receive. 1, 2, 4, and 5 are used for tip and ring transmit and receive on a T1 wire cable. So it's RJ48C instead of RJ45. crossover cables for Ethernet won't work as a crossover cable for a T1. Again, pins 1, 2, 4, and 5 need to be crossed over in order to interconnect to T1 devices over an RJ48C connection. And the signal that's going to go across that cable will be a 1.544 megabit per second signal. That's the speed of a T1. That 1.544 meg is composed primarily of 24 64K signals. A 64K signal is called a DS0 or a DSO. A T1 is a DS1, and it's a multiplex of 24 of them. 64K is the amount of bandwidth required to carry voice, uncompressed. So G.711 codecs, the most common codec used to encode voice digitally to carry it over a T1, or for that matter to carry it over an Ethernet network for voice over IP. G711 codecs convert a voice stream to a 64K, an analog voice stream to 64 kilobits per second of data. So 24 of these are multiplexed together to make a T1. A T1 is basically 24 64K channels. If you do the math, 64 times 24 is 1.536 meg. There's an extra 8K of overhead that's used for framing on T1s. Basically, they're special bits that are used to mark the beginning and the end of each frame so that the receiving equipment knows which bit corresponds to which of the 24 DS0s. So there's a special framing pattern sequence that's inserted into those overhead bits to allow the receiving equipment to sync up to it. The two devices on a T1 are synchronized. The T1 lines are always synchronized, one device providing clock to the other. One device provides a 1.544 megabits per second clock, and the other device will recover it as long as it's within 50 hertz. So if devices aren't quite, if they aren't perfectly calibrated, the clock's a little bit off, link will still come up as long as it's within 50 hertz. Typically, you're going to be within 4 or 5. Hopefully, you're within 1 or 2 hertz of it if the device has been calibrated recently. But even if not, as long as it's within 50, that's spec, and T1 link should come up. You want to be careful that you don't option two pieces of equipment on the same link to both be internal clock, though, because they're going to expect to receive clock at the same rate they're transmitting it, or receive data for the same clock they're transmitting. You end up getting bit slips and bit errors. So we'll take errors on a T1 if both devices are set up for internal clock. Normally one should be set up for internal clock and the other recovered. Network equipment normally has a third option called external, which internal or external will both enable that device to provide clock to the device it's connected to, but external would mean it's deriving clock from a bits clock, a third input. So you're bringing clock into the device, and instead of using its internal oscillator, it's using that external clock source in order to provide a clock across the T1, and then the device on the other end of it will recover it. So that's one of the key settings when you configure a T-BERT, an HST-3000, for that matter, your network equipment, whether it's internally or externally clocked or recovered. And most of the time, if you're testing from a customer site, you're externally clocked to recover clock. If you're testing from network towards the customer, you're internally clocked, or maybe you're pulling clock in from an external clock source, but you're going to provide the clock to the device at the customer site. A second key setting when you're configuring your equipment is framing. There's two standards. There's two common standards. There's more than that, but there's two most common standards for framing on T1s, and it's called D4 and ESF. D4 is an older standard. It has some limitations, especially when it comes to transmitting data as opposed to voice on T1s. So most T1s that are provisioned today use ESF, which is a newer standard. The difference is how the framing bits are defined. We mentioned earlier that a T1 had 24 64K channels, so it's a multiplex of 24 channels, and then there's extra overhead for framing. There's a framing bit for every 8 bits transmitted on each channel. And the framing bit, again, has a framing pattern sequence and some other, functions built into it, but the main thing is it allows the receiving device to get frame synced, to sync up to the receiving traffic coming in and to know where channel 1 is, where channel 2 is, where channel 24 is. So it identifies the frame bounders. For ESF, it also gives an error check. But the layout of the framing pattern sequence is a little bit different for ESF versus D4. So you have to know that going in. Or you can auto. Our test sets will auto, but that is something that you can configure on your network equipment as well as your test sets. Again, ESF being the most common standard. The third primary thing we got to set up when we set up a test set or meter to do testing or in your network equipment is line coding. Line coding is basically how you represent ones and zeros in that 1.544 megabit per second signal. The original line coding method for T1s was AMI, stands for alternate mark inversion. With alternate mark inversion, a pulse was sent for ones, and then no pulse was sent with zeros, and then another pulse was sent with opposite polarity for the next one. So ones were marks or were pulses with either +3 or -3 volts, and adjacent ones always reverse polarity. Noise, if there was noise on the line, it could be easily detected because you would have 2+ voltages in a row. For instance, if I had a little noise spike here, and that's a special error case called a bipolar violation. But by alternating the marks, it allowed for error correction. It also meant that DC buildup wouldn't occur on the lines, so it allowed you to go over much longer distances. The main problem, though, with this is that if very long strings of zeros were sent, the ones were required in order to recover clock. Remember that one device is internal or providing clock, the other device recovers it. These one pulses are used to recover the clock, so they have to occur at fairly regular intervals in order for the receiving equipment to get a phase lock loop. For voice, that was addressed by never encoding voice as all zeros. You always inserted ones in certain points. A codec will always insert at least a 1 out of every 8 bits when it's encoding voice. But for data, you could have long strings of zeros. So AMI wasn't real good at sending 64K data. So B8ZS was introduced to better handle data applications at 64K. And what it did was when there was a string of 8 zeros, it substituted a special pattern that has bipolar violations in known locations. And then receiving equipment would know if it saw, hey, a bipolar violation, 4 bits out, and then another one immediately following that it substitutes all zeros for that instead of treating these pulses as ones. So that allowed devices to maintain their clocking even if there were long strings of zeros if data was being carried on a T1. B8ZS is what's used by almost all modern equipment today, but for older installations where you're either maintaining older equipment or you're upgrading service but still providing it into an older piece of equipment, you may still have AMI and D4. Usually AMI and D4 go hand in hand, and ESF and B8ZS go hand in hand, but it doesn't always have to be the case. I think in my 20-some years of testing T1s, I've come across one case where they were mismatched. Let's take a quick look at one of our test sets and see how this stuff is set up. So the T-BERT 5800 has a quick config where you can set the framing. So I can switch between ESF and D4 framing right here. I can switch my clock source in the actions panel too. So 2 of the 3 are right at my fingertips without even going into setup, but under Setup, when I set up my T1, I have a few different tabs here for the BERT test I'm doing. The Interface tab is where I can set my clock, internal, recovered, or external. I also set my line code here, B8ZS or AMI. And then in the next tab, I set my framing, ESF or D4. So very easy to set them up in the T-BERT. Likewise, in the HST-3000, I go back to my home screen. And then configure. The configuration menu for the HST has different soft keys to set up different things. Summary has some of the most commonly changed settings. So right in the summary screen, I can change my framing. And under the DS1 screen, I can also change my framing. In addition to ESF and D4, there are a few other options here, but I'm going to leave it at ESF. My line coding, I have B8ZS and AMI, and finally my clock source, internal or recovered. So those are the main three settings. When you're monitoring a T1, or for that matter, when you're terminating it to run a test, T1 could be in an error state. So there's a number of different errors that are defined on T1s that you always want to look for when you're running a test, and they're defined on this slide. For starters, you can have loss of framing. We said there were two framing options for T1. It could be ESF or D4. And if you're not seeing the framing pattern sequence coming in, then you have loss of frame. Loss of signal, I guess, is worse. You're not even seeing the T1. You're not seeing pulses coming in, and that you can get a phase lock loop to, and and see a 1.544 megabits per second signal. But if you have a signal, then the next step would be to get framing, which means you see the framing pattern sequence, and then you're locked into the T1. You can see the traffic coming in. A bit error is another type of error for when you're doing bit error rate testing. It's going to tell you that you've taken an error for your bit error rate test. We mentioned bipolar violations already, but that's if you don't, if you see two adjacent ones that are both positive pulses, or two adjacent pulses in the same direction. That's a bipolar violation. It's usually an indication of noise on the line. A CRC error is only available with ESF, but it's an indication that there's been bit errors in a T1 frame. A frame error is another special case of a bit error, but it's a bit error that occurred in the framing pattern sequence. And if you get 2 out of 5 frames in a row with frame errors, you get frame loss. Finally, there's errors associated with excess zeros. I mentioned that you need consecutive, you need a minimum ones density in order to maintain a phase lock loop and keep timing on a T1. So too many zeros in a row is another error condition. So these are all things that we're going to look for on a T1 when we're running a test. Finally, there's a few different alarm conditions that the test sets will look for as well. Primarily, the alarms are yellow alarm, red alarm, and alarm indication signal. A yellow alarm is sometimes called remote alarm indication. And if you're getting a yellow alarm, it means that the T1 coming to you, you're receiving a good T1. There's not necessarily any problems on the T1 coming to you, but the device you're connecting up to is in red alarm. It basically is in a loss of signal state. If it's not getting signal, it sends back yellow alarm. If the T1 is then mapped through beyond that device to another device, this section of the T1 is up, but it doesn't have any content or any payload to send it, so it just sends an unframed all one signal to keep the link up. and the receiving device that sees that signal goes into a state called alarm indication signal. It's an AIS. That's what it's receiving. So red alarms, yellow alarms, and alarm indication signal are the three alarm states that we can look at. We can see these either whether we're doing in-service monitoring, so you plug into the monitor ports to just look at a T1, or if you're doing out-of-service testing. And that's what we'll look at next. We'll go through next is the main out-of-service testing application, which is bit error rate testing. We've already looked at three primary settings you need to do a T1 bit error rate test, and that's your clocking, your line coding, and your framing. The fourth thing that you need to set up to do a BERT test, which is one of your primary tests on a T1, is to select a BERT pattern. There's a number of patterns available. I think there's 50, maybe more than that, over 50 selections available for T1 for BERT patterns. A few of the key ones are shown here. Delay is an important one because if you set the pattern to delay, instead of getting a bit error rate, you get round-trip delay measurements. There's an option called live, which you use for in-service monitoring, where you're not looking for bit error rates as well. But then the rest of the options, for the most part, are designed to give you a bit error rate on the circuit. QRSS, or quasi-random signal source, is a very common first test pattern to run in order to test out a T1. And it simulates live T1 data, and again, it's a very common starting point to test out a T1. But there are some special cases that a QRSS pattern might not detect, so we always recommend doing multi-pattern testing when you're doing a T1. 3 and 24 is another pattern that's available. It means basically 3 out of every 24 bits is a 1. So you can never have more than 15 consecutive zeros, so it doesn't violate the 1's density, but it is the very lowest 1 density that's allowed. 1 and 7, or 1 to 7, or sometimes referred to as 1 and 8. It's 1 out of every 8 bits is a 1. So it's minimum 1's density for B8ZF. An all 1's pattern can be sent where you're constantly doing plus 3 volts, minus 3 volts, plus 3 volts, minus P volts. So that can stress T1 repeaters and other devices because it's a stressful pattern for alternating the current. An all zeros pattern. All zeros pattern should invoke B8ZF constantly. On an AMI link, you can't send all zeros. It's a violation, but on B8ZF you can, but it'll constantly invoke the B8ZF substitutions. So that will very quickly detect if you have anything on your circuit miss option for AMI. And then there's several other patterns available as well. Little flow chart I have shown here, which is a recommended sequence to be able to detect different types of errors on a T1. But starting out with a QRSS, if it takes errors, it could be hardware trouble or a B8ZF AMI miss option. So by doing a 2 and 8 and a 1 and 7, you can narrow that down. But if a QRSS passes, then by doing an unframed 1 and 7 and an all zeros pattern, then you can complete the test and know that it's clean. So those three, if they pass, will indicate a good link for B8ZF service. But errors at different points can narrow it down to hardware problems or optioning problems. Bit error rate testing can be run head-to-head. It can also be run to a loopback device. Loopbacks could be hard loopbacks where you just basically have a point on the link where you're tying the circuit back to itself. Transmit to receive. You just have a jumper interconnecting the two. In that manner, you can be testing back to yourself. Or it can be done using loop codes. The different devices on a T1 circuit, some are loopable, and there's special messages that are sent, special patterns that are sent, either in the framing bits or in the payload, that will put certain devices into a loopback, and then you can test to it in that manner too. I'm going to show examples of the top and the bottom. When you're doing a bit error rate test, 3 key areas of focus. We start out making sure that we get a good signal coming in and the frame sync LEDs turn on. the summary page to turn green on the test set. Then we can loop up the far-end device and send an error to make sure that it's looped back to us, and then run the bit error rate test. And that's what I'm going to do now. In order to do that, right now I have a HST-3000 and a T-BERT 5800 connected together through a CSU. So I have a little add-trans CSU here, and coming out of the transmit and receive ports on my HST-3000, I'm coming into the jacks labeled equipment in and out, and then out of the transmit and receive jacks on my T-BERT 5800, I'm in the network in and out jacks. These are basically interconnected through the CSU. If I wanted to monitor this with a third device, I could plug into these two monitor jacks here. The CSU is loopable. So testing from the network side, I can send a loop code in it and put it in the loop and test out this side of my circuit, or I can test through it to the HST-3000. I could, for that matter, loop up the HST-3000, or I could test head-to-head between the two. But those are the different test examples I'm going to show you now. So let's start out with the T-BERT 5800. To get to this screen that I'm in now, when I powered up the T-BERT, I selected a test. I went to the DS1, DS3 test selection. From there, I can do DS1 or T1 as well as DS3 tests, and I selected DS1. Under DS1, I have a number of different test options as well, but I did DS1 BERT, and I selected Terminate. It's grayed out because it's already selected. But the other option in here would be Dual Monitor. Again, if I wanted to plug into these monitor ports, I could select Dual Monitor and then just receive signals in on both of those T1 ports and see if it's an alarm, see if any errors are occurring, but I can't transmit anything across it. I'm just receiving. But I'm going to go with DS1, DS1 BERT, and Terminate. It's already selected, so that's what I see when I click on this tab here. My quick config, again, lets me change my framing, lets me change my test pattern, my BERT pattern. I can auto to what I'm receiving, what's coming in. And it's going to tell me, hey, it's the text ESF, and it's getting a QRS pattern, so all that can be automatically configured. Or it can be configured under the Setup button. Under Interface, I select that I'm terminating as opposed to monitoring a circuit. If I'm monitoring, I could be either bridging it or I could be at a DSX monitor point. Bridging it means basically I'm using alligator clips to just clip onto the metal. So I'm just bridging the line. And if I transmit it when I'm bridging, I'm going to bring it down. So you got to be careful when you're working in bridge mode. But DSX monitor is when you're using a CSU or a DSX panel that has designated monitor jacks that are resistor isolated so that you can't bring the circuit down. But I'm going to terminate, in order to do a bit error rate test. I'm set up for BAZS. I'm going to provide clock from this T-BERT since it's the network side. I could insert a clock offset if I wanted to see if if I'm off by 50 hertz, does that equipment still tolerate it? If I wanted to, kind of find the thresholds for tolerance, you can do that. And finally, you can add some line build out. If you don't want to send out a 6-volt peak-to-peak signal, you can attenuate it. Under framing, I can choose between ESF and D4, and then under payload, be either bulk or fractional. Bulk is full T1. Fractional will just be testing individual DS0s. So if instead of having a full T1, I only had 256K, so 4 64K channels, you could do that as well. Just test those 4 channels. I'm going to leave it at bulk. Under pattern, I have all my patterns available here. We're going to do QRSS, but I have several others available here, including down at the bottom here, delay and live. Under loop, I can choose what type of device I want to loop up. So we can loop up HDSL equipment, we can loop up CSUs, smart jacks or NIUs, repeaters, MSSs, or you can do user-defined loop codes as well. I'm connected up to a CSU, so I'm going to loop it up. There's actually a couple different types of CSU loop codes that we support. Basic CSU works with almost any CSUs. ESF only works with ESF. It doesn't work with line 4, but you can loop up the line side or the payload side. And I don't need my T-BERT to respond to a loop code, but it could respond to a loop code and loop up to an incoming loop code as well if I wanted it to. Does service performance testing, service disruption test, performance testing. You can do time tests as well, but I'm just going to focus on these settings. So I'm going to go back to results now. In the actions panel here now, I can tap on loop, and I should be able to loop up that CSU. Loop up successful. If I can go back to results now, if I insert an error, it should come right back to me. Sure enough, I just sent myself 3 BPVs. If I send myself a bit error in my QRSS pattern, I should get some bit errors as well. So it's looped up and it's running the BERT test. So at this point, I could loop down. Now the CSU is no longer in loop. It's testing. It's passing traffic straight through. And on the other side of the CSU is my HST-3000. So let me bring it up. I'm going to hit the restart button to clear it out. And we'll take a quick look at its configuration. It's set up for ESF, B8ZS, and QRSS. It should be recovering clock. And it's set in the QRSS pattern. So right now it's saying all results are okay. I can insert an error by hitting the 1 key. And, hey, the error came through. Likewise, I could insert an error over here, and that should get to my HST. So now I'm testing head-to-head through the CSU from T-BERT to T-BERT, or from T-BERT to HST. Now, there's a variety of displays I can look at on either of these. I'm going to start out with the LED panel. So I have an LED panel showing on both of my units now. The first LED is signal present. As long as I got a clock coming in, I'm going to get signal present. So loss of signal would make me lose signal present. B8ZS detect is going to be detected if it's seeing a B8ZS signal. So if it's seeing B8ZS substitutions. So one easy way to get rid of that is to send an all ones pattern. With all ones, B8ZS is never invoked, so hey, I still have a signal present, I still have frame sync, but it's no longer getting B8ZS. History tells me that in the past, before I just made that change, it was getting B8ZS. It also had pattern sync because it was getting a QRSS pattern. I have different patterns being sent now. This is sending QRSS, this is sending all ones. So I no longer have pattern sync, I no longer have B8ZS, but I still have signal present and frame sync. Frame sync is lit on both of them because they're both sending ESF framing. If I change this to D4 framing, now I no longer have frame sync. I still have a signal. I'm getting in a T1 signal, but it's not framed the same as what I'm configured for. I'm expecting to see ESF framing on my HST-3000. I have D4 framing coming in, so no frame sync. I'm going to hit the restart, clear out the history here, and we'll bring them back one at a time. So now I no longer have a framing mismatch. So we have frame sync on both units. Now I no longer have a pattern mismatch. So I have all green LEDs now. Other results I can look at are available on the HST-3000 under the display soft key. So I can look at signal, interface, BERT, LED, etc. We'll take a quick look at signal. Here I see I'm getting a receive frequency of 1.543998. So I'm just 2 or 3 hertz off. The signal's a little strong, 1 dB DSX. So 6.73 volts peak to peak. So the CFU I'm using is putting out a little bit hotter signal than standard T1, but it's not enough to hurt anything. But as I look at different display options, I can see the interface. I'm not getting any bipolar violation. I've had 1 frame loss. My BERT results, everything's clean, so I can see results by either hitting the right arrow key to scroll between the different display options or by choosing a particular display option. Normally I leave it at summary, and then if I see errors, then I start to drill down and look at the more detailed results. Now the T-BERT gives you the luxury of 2 simultaneous displays, so normally I always leave one at summary status, and again, that stays green as long as I'm not taking errors, and then on the second one I can drill down. Under summary, I also have an event log. Basically, whenever I take an error, it's going to be time-stamped and saved in that log. I have a histogram which really shows the state over time. For instance, if I went into a loss of frame now, you can see I have frame sync loss and an alarm, and so errors over time are graphed. Under the interface category, I can see all my signal results. I'm getting a 1.544 megahertz signal, 6.12 volts peak to peak, no bipolar violations. I scroll down, I can see my clock sources internal. See DS1 results. Any alarms or errors that have occurred. I can get different in-service measurement assessments. The LOS ones here are for out-of-service. The in-service measurements are for BERT tests. Let me choose one of them. It'll give me an assessment based on the G826, the ITU spec for verdicts on a T1. So, depending upon the bit error rate, it's either going to be accept or reject. If I got a very high bit error rate, this would go to rejected. Or if so it gives me a pass-fail assessment based on G826. Next, under payload, I get my bit error rate. I can also see the traffic, see the different channels. So just see the zeros and ones. Normally, for bit error rate testing, I leave it at summary status and BERT. Then if this stays green, and I have zeros here, I know my test is clean. But that's T1 BERT testing in a nutshell, either head-to-head or the loopbacks. So at this point, I'm going to go back to the Q&A and the chat panel and see what questions come up, and then we'll move on to some other T1 tests. Okay, have a when doing head-to-head testing using layer 2 to both HSTs need to have IP address set up. Okay, everything we've discussed so far is for layer 1 testing. A bit error rate test is layer 1. There's no layer 2 addressing, no MAC addresses, nothing. We're just basically testing out the cable and layer 1 equipment like CSUs and repeaters. Layer 2 tests and IP addressing is going to come into play in the next thing we discuss. So that's a good segue to the next section. Any other questions? Okay, well, we're going to cover T1 MPLS, then we'll cover a short break. Then we'll do a short break. Okay, T1 MPLS is a switch service offered by many service providers as a replacement for frame relay. The T1s were originally deployed either to carry voice between central offices or between customers and central offices to the PBXs, or as data connections between routers. If it was a data connection, it's expensive in that the tariffs, the charges were based on basically speed and distance. If you paid 24 hours a day for the service, you have a nailed up 1.5 megabit per second link, whether you used it or not. So it's an expensive service. The frame relay, and before that X25 public data networks, and even ATM were alternatives where you could get a given access rate, but you didn't have to pay the premium that you would for leased lines like T1s. Frame relay is still around, but providers are maintaining separate networks for frame relay versus Metro Ethernet, and all the growth is in Ethernet these days. So instead of maintaining separate networks, what T1 MPLS allows is to have a T1 access into a central office or into a point of presence or whatever, and then using an MPLS core network to make the connections and get the inner office traffic utilizing the same network as Metro Ethernet. So T1 is on the access, and then it's an MPLS backbone to get to the far end location, and then T1 again out to the other customer location. And for that matter, it could be Ethernet on this end. You can mix and match the two. Layer 2 for T1 MPLS is called point-to-point protocol. It's analogous to Ethernet. Like Ethernet has MAC addresses and a frame check sequence in the Ethernet frames. For T1 MPLS, you also have frames that are going across it, and they have addressing information and frame check sequences and type fields in them. And they carry IP traffic with an IP header with IP addresses, just like on Ethernet. It's just a different protocol to define what the frames look like and how the IP traffic is carried. So there's PPP or point-to-point protocol. There's also multi-link PPP or multi-link point-to-point protocol that can be used to carry the traffic. PPP would be just a single T1. Multi-link PPP would allow you to do this with multiple T1s. So two T1s could be combined to provide a 3 meg service. So the protocol stack looks a lot like the IP protocol stack does for Ethernet. The main difference is the physical layer and the data link layer are different. For network access, again, it's a T1 at the physical layer, and then PPP and MLPP for the data link. then you still have IP traffic and TCP, and you could be sending your same IP protocols across it for file transfers and mail and web access and everything else. It's just across T1 MPLS network access. You still have control plane applications, and processes controlling everything, and user plane traffic. So network and above, it's the same. It's just a different network access. Testing this, again, you still have some of the same peer areas of focus on the T1, and that you need a good signal, you need frame sync, summary screen should turn green, you want to make sure you're not an alarm. You can BERT out the T1 to make sure that it's clean on the access loop, but our T1 MPLS application on the T-BERDs takes it one step further and allows you to do ping testing and allows you to do protocol analysis. BERT, nothing's changed from what we just covered. BERT out the T1's the same, but the T1 stops at the label edge router once you hit the MPLS network. So you can't run a BERT test all the way across end to end. Once it hits this label edge router, instead of a BERT pattern, that expects to see PPP IP traffic that can then be distributed across the MPLS core. BERT patterns aren't going to make it across the core. They're not formatted properly. So a BERT test only tests out the access loop, and it could be run independently on each end here. But to do end-to-end testing, you have to send MPLS frames and IP traffic so that it can be label switched across MPLS end-to-end. We can do that with the T-BERDs. To do that, I'm going to do a direct test between just T-BERD to T-BERD. Don't need a CSU in place, but I'm going to set up my two T-BERDs in order to do this. Actually, in the interest of time, I'm just going to loop back a T-BERD to itself to be able to show the key stuff to you here. So give me a minute here to change my cables around. And I'm going to switch over on my T-BERD 5800. Select test. Still DS1, DS3, DS1. And here I'm doing a DS1 PPP test and a ping. And I'm going to terminate. Okay, to set up a ping test across the T1, let's start out in the setup menu. I still need to set up my interface for B8ZS for internal timing and ESF framing. My payload is bulk as opposed to fractional. I could do either. But now I have these HDLC and PP and IP tabs to set up. So under HDLC, I'm going to just leave everything at default. It's just normal HDLC mode and the normal CRC or frame check sequence. I can set myself up as either a client or a server in PPP mode. A client connects up to a server, so it's one end of the circuit's a client, the other end's a server. And then there's different types of authentication that you can do. I'm just going to disable that for the purposes of this demo. IP mode, I can have static IP addresses or DHCP. Once I set it to static, I go to the IP tab, and here is where I set up all my IP addressing. So I have a source IP address of 192.168.1.11, and then I enter a destination IP address I'm going to see if I could just ping myself. So now back in results, I see I have signal present. I see I have a frame sync. I have a variety of results I can look at here for HDLC statistics, PPP statistics, and then most importantly my ping statistics. And I can turn the client on, and if I was connected to a server at this point, I would be able to do ping tests and verify connectivity across the network. Since I don't have a server, it's timing out. So that's MPLS. At this point, we can take a short break, and then we're going to switch over to ISDN primary interface. We're going to talk about the two different business voice services. So the rest of the session will be ISDN primary interface and voice over IP, SIP trunking. So right now it's 2:27. I want to keep this break short. We're going to keep it to 5 minutes. So at 5 minutes from now, I'm showing 2:28 now on my clock, but 2:33 promptly I will start back up and we'll go over ISDN PRI. Before doing that, if there are any questions on MPLS, I can take them real quick, or I can take them over the break. But we'll get started up in 5 minutes again. Okay, welcome back. This is Dave Baker with JDSU, and we'll get started back up here. Let me check real quick if any other questions came in over break, and doesn't look like it. Wait a minute, I do have some questions. Which option do I need on the T-BERT 5812 to do DS1 PPP testing? Let me bring up my my T-BERT and I'll show you. That just came out recently. Actually, the release that's just come out has it. So if I go into Tools here and Review Install Options, my demo unit has everything checked off on it, so some of these are things that might be of interest, but a lot of them are rarely used options, like the op-size stuff. But I think it's down near the bottom here under PDH interface options. C5 DS1 DS3 HDLC lets you do HDLC analysis, including the ping. We also support capture decode. Actually, I forgot to show that to you. But when you're doing either a ping test or when you're just monitoring, plugged into monitor ports on a T1 link, you can capture the traffic into a PCAP file and then view it using Wireshark, either right on the T-BERT itself or by exporting it to a thumb drive or whatever to bring it into your PC. So we save into PCAP files, and then you can look at protocol decodes of the traffic on PPP. So these are the two options associated with that, either HDLC capture, which gives you the packet capture and decode, or C5 DS1 DS3 HDLC, which lets you do ping testing and gives you some basic statistics if you're monitoring. I don't see where you set up for DS1 PPP. Yeah, you probably don't have that option on your test set. Again, that just came out. So, yeah, unless you just received your unit, you won't have that, but it is something that's available as a software update. If you have it, so again, it'll show up in the Tools menu under Options and also under Select Test. When you do DS1, DS3, and DS1, you have either HDLC dual monitor, which will let you do capture and decode, or the regular PPP, ping, terminate. And then the terminate application, once again, or what I didn't show you before, it does have the capture. Any of the traffic you send or receive will be captured, and then with Wireshark, you can look at the decodes. So this is a Wireshark capture I'd done previously. Wireshark is a shareware protocol analyzer at wireshark.org. You can download software to be able to do this on your laptop, but in order to capture it on the T1, you need a T-BERT. But this is showing me all the different traffic hello packets and padding packets and the different messaging to bring up the link. So Someplace in here there should be the pings. And maybe I didn't get that far in this trace, but it just bakes down the messaging between the two devices on the PPP link, packet by packet. Okay, well let's move on to ISDN PRI. To switch to that test, I'm going to go into Select Test. Still under DS1, DS3, the DS1, and DS1 ISDN PRI, and terminate. Then on my HST-3000, I hit the Escape key to back out of BERT, and OK to get to this menu, but now instead of selecting BERT, I'm going to select ISDN PRI. So ISDN PRI is a business voice service that supports 23 simultaneous calls. Now, it uses a T1, typically with ESF framing and BHCS encoding, although it can be AMID4, just like any T1. T1's 24 channels. We can only do 23 calls because one of the channels is used for overhead to set up and tear down the calls. That channel is called the D channel, and it's almost always channel 24, and then the other 23 channels, channels 1 through 23, are called B channels, and they carry the voice. So you place a call, it's set up on channel 24, and then the voice is carried on one of the 23 channels. You set up a second call, channel 24, the D channel still carries the messages to set up that second call, but it's going to be assigned to a different B channel. Traditional ISDN deployments are done over, say, repeater T1s or HDSL, but a T1 coming from the telco would hit a line card in a classified switch, which in ISDN terminology is called an NT, or a network termination device. Cross-connected through a DSX1, which would have your monitor points and your cross-connects, and then you carry it across copper to the customer site. A network interface unit or a smart jack would be the DMARC. Customer may or may not have a CSU before it hits their PBX, which terminates the ISDN calls, the PRI calls. In ISDN terminology, the customer device, the PBX, is called a TE, or terminal equipment. And the PRI runs from the central office to the customer as a T1. ISDN PRIs can also be deployed using Ethernet and voice over IP networks by installing a device, customer site called an IAD, or Integrated Access Device. There's several companies that make these: Cisco, Adtran, Edgemark, to name a few. But basically, they will allow you to still support ISDN PRIs, but take advantage of a Metro Ethernet or voice over IP access network in order to provide that to a customer. In this case, the ISDN PRI exists between the customer's PBX and the IAD. It's a T1, so it's a T1 cabling. It might be going across a 8-pin modular jack, Cat5e or better cabling, but it's pinned out as a T1, as we described earlier. It's not an Ethernet connection. The D channel carries the signaling to set up and tear down the calls, channel 24, and then the other 23 channels will carry up to 23 simultaneous voice calls. The IAD, though, converts it to Ethernet. So the network interface on the IAD is an Ethernet connector. Could be connected up to a DSL modem or a cable modem or a layer 2 switch, and going across an access network to the central office or head end, at which point it hits a router, and it's then sent to a communication server that then converts it over to SS7 and out to the public switch telephone network to set up and tear down the calls. So the T1 PRI only exists at this point, and then it's pretty much Ethernet from there up to the edge of the service provider's network. The protocols that are used for PRI consist of a call control and then the voice itself. The call control is basically the messaging to set up and tear down the calls, and most of the equipment that's deployed today uses a call control standard called National ISDN. National ISDN's been around for, gosh, I don't know, I'm guessing 15 years or so. But before National ISDN, there was a recommendations. There was a standard put out by the ITU called Q931, but every equipment manufacturer implemented it a little bit differently. So there's international variants that only work in England or France or Germany. And then in North America, there were two different variants also. AT&T with its 5ESS switches, or now Lucent, had one variant and implemented it one way, and Northern Telecom, or Nortel, implemented it another way for their DMS series of Class 5 switches. And they were incompatible. So a customer had to provision their PBX to work in one way or the other, but it had to be reprovisioned or get a new software load to work with AT&T versus a Nortel, a Lucent versus a Nortel switch at a central office. So it caused compatibility issues. It made it very difficult for customers to migrate also. If they wanted to switch from one service provider to another, they had to make sure they had the same switch type. So it was deemed anti-competitive, and National ISDN came about, which is a common standard for all network equipment manufacturers. So that defines the messaging to set up and tear down the call. It's carried over a data link, just like IP traffic is carried over an Ethernet data link or a PPP data link. So the data link that's used for the D channel to set up and tear down the calls is called LAP-D, or it's defined in a standard called Q931, and then it's carried over to T1. So the D channel, channel 24, has these protocols associated with it. The voice on the B channel isn't really a protocol, it's just 64K encoded voice carried on the T1. Layers have to come up in order. So the T1's got to be active for anything to happen. Calls need to be placed before there's any voice. But in order to place calls, first the T1 has to activate, then the D channel has to activate, then you can make calls. So that's kind of the steps that we're going to take in testing too. Make sure the T1 comes up properly, make sure the data link comes up, and then place calls using the National ISDN call control standard. If you've taken any Ethernet classes before, you've probably seen similar pictures of this for what Ethernet frames look like. Ethernet frames have MAC addresses in them, a destination address and a source address. They have a type field, and they have a frame check sequence at the end to detect errors. Same thing applies to the data link for ISDN PRI. It's just that it's laid out a little bit differently. It has a field in it called a control field that defines different types of frames that are used to establish the data link. I'm not going to go through every different frame in here and define them all, but in summary, there's information frames that are used to carry signaling messages to the National ISDN messaging. There's receiver readies that are keep-alives that are sent when the link's idle, just to keep the link active. And then there's other messages that are used to either flag errors on the link or to bring the link up initially. The basic message is saying to establish a link involves the TE, or the PBX, or in our case, the test equipment, sending a message into the network called a SAVME, a Set Asynchronous Balanced Mode Extended message, which basically just a wake-up message saying, hey, let's establish a link here. And it's supposed to get an acknowledgement back called a UA message, or an unnumbered acknowledgement, and at that point the data link's up and you're at a point you can place calls. So you don't necessarily need to see all this happen, the message exchange on the T-BERT or the HST, although you can. But the main thing you want to look at is that you do get to the state called multi-frame established, which it means the D channel came up and you can place calls. After that, at the data link, it's just information messages and then keep alives that are sent across the link. The information messages will be sent when somebody places a call or disconnects the call. And there's a number of different message types defined for that. In the National ISDN standard or in Q931, you have things like setup messages, setup calls, and disconnect messages to tear down calls, and then other messages to show other steps along the way to either set up or disconnect a call. Messages carry additional information elements depending upon what the message is. For instance, a setup message has to carry the calling party number and called party number. Disconnect messages have cause codes in them indicating why a call is disconnecting. It might just be that the user went off hook and it was normal clearing, or it might be because of a network issue, and that's indicated in a cause value. So the HSTs and T-BERTs transmit all this information properly formatted in order to make sure that you can place and receive calls when you're doing a turn up, and they can also be used to monitor incoming traffic and can show all this information to you as well to troubleshoot problems. The basic message exchange for an outgoing call is to send a setup message, wait for a connect message, then you can speak and listen, and then you go back on hook and you send a disconnect message, and then you get a release and release complete to finish tearing down the call. For incoming calls, you'd receive a setup message, send back an alerting when it's ringing, a connect message when you go on off hook, get an acknowledgement, and then when the call disconnects, get a disconnect message, and then you acknowledge that. So the key areas of focus for testing PRIs, again, the layers have to come up in order. So first, verifying the T1 provisioning. Next, verifying the D channel comes up, and then making sure you can place and receive calls, and thereby proving connectivity to and beyond the Class 5 switch or the communication server. Calls can be placed to any device on the public switch telephone network. You don't have to place a call to another PRI device. You can place a call to your cell phone, to your mother, to your girlfriend, anyone with a phone you can place a call to. But it's common for service providers to have a calling plan to do on turn-ups, and you can save that calling plan into your equipment and call all the numbers. Might involve calling N1 numbers, N11 numbers such as customer service at 611 or information at 411 or even 911 in some jurisdictions. They'd like you to make it a call to E911 and ensure that that's working properly. Just notify the 911 operator that's a test call on a new turn-up. But in some markets, they discourage you to do that. You only call an emergency, but that's kind of up to your own standard operating procedures based on the district you're in. Finally, you can do packet capture and verify proper signaling for the messages as well. So those are the things I want to show you now. To do that, I have an HST-3000 and a T-BERT 5800 interconnected. I'm still going through the same CSU, but that's kind of irrelevant. One of these devices is going to be set up as a TE device, so as a customer premise device that's going to place and receive calls from a customer premise. The other is set up as either the IAD or the Class 5 switch that I would be connecting up to from the customer across the access network. So the HST-3000, again, I've already launched it, and I did that by selecting ISDN PRI from the test selection screen, and the screen's gone green, so far so good. The T-BERT 5800, I launched it under the Select Test menu by selecting DS1, DS1, and DS1 ISDN PRI, and terminate. Again, it's grayed out because it's already selected. So when I click on this tab here, I'll see the results. And I'll hit restart, and it'll all green up. Now, I want to verify that the T1 came up properly first, and I can see that by looking that I have signal present and I have frame sync. And yeah, the green summary results OK screen tells me that as well. But if I did have issues with my T1, say I didn't have T1 framing, I would have to resolve that before I could do anything. My D channel's not ready now. I can't place and receive calls. My actions are grayed out over here. I can't place and receive calls either. I got to get that T1 up and the D channel up before I can do that. So when I go back to ESF here, and now my T1's up. And now my D channel's ready. And now I can dial calls. So on the HST-3000, the LED display is useful for making sure my T1's up. I have signal present and frame sync and D channel ready to troubleshoot things. If it doesn't come up, I can look at signal issues, make sure I'm getting a good clock in. I can look at my interface and see if I'm taking different types of errors, like bipolar violations or CRC errors. In ISDN, I can see, hey, I am at the multi-frame established state, or I am receiving frames, or I'm transmitting frames and not receiving, so I can get information about the different types of frames that are coming in. So those screens can help me troubleshoot if I don't get to the state where I can place and receive calls. But then once I am, I can go to the call screens to place and receive calls, or for that matter, go to the summary screen and do it from there. Likewise on my T-BERT, I can look at my LED panel and see I have a signal present and frame detect, and the D channel's up. But I have a variety of results I could look at here to troubleshoot why I'm not getting a signal present or why my D channel's not activating. Okay, so D channel is up. Haven't really looked at the setup menus yet, so only would have to do that in order to get the D channel to come up properly, although the default settings work for the most part. But let's go ahead and look at the configuration menus here. On the HST-3000, the summary screen lets me set up that I'm terminating the circuit. It's B8ZF ESF. I'm emulating a TE. Again, remember we said on an ISDN circuit, you always have a TE talking to an NT. So since my HST is a TE, when I set up my T-BERT 5800, I made it the NT. If I had a TE talking to a TE, let's see what happens. For that matter, let me do it this way. I'm going to make an NT talk to an NT. I go to results. My D channel's not ready. I still have a signal present in frame sync. The T1's good, but the D channel's not going to come up. You have to have a TE and an NT talking to each other. Now my D channel came back up. Call control is set to national. I also have options in there for DMS and 5ESS. Channel set to any, so it'll go out on any it'll just go cycle through the B channels. There's more detailed settings under the other keys. For instance, under DS1, I could set things like line build out. The TE recovers clock, the NT provides it. Under ISDN, I can set different numbering types and numbering plans, but typically I leave all that stuff at the default. Under call, there are some important settings here that you do have to change every time you're testing a PRI. The most important two are directory number and number to call. Directory number should be set to the customer's billing telephone number. So whatever the billing telephone number is for that site that you're turning up, or if you're an end user, whatever your billing telephone number is, you put there. And then for number to call, whatever you want to put your first test call through to. Maybe it's your cell phone. Make sure you can receive a call and place a call off network to your cell phone. There's another option on the HST that's not available on the T-BERDs, and that's the dial mode. HSTs can make 2 simultaneous calls. That's what dual call is, but can also do multiple calls where you can make 23 simultaneous calls. There's a couple extra menus in the GUI to look at to do it, but you can place calls on all 23 channels. I'm going to leave it at dual call initially, and then we'll revert back and look at multiple call. I can also set up a phone book. Let's see if I have one in here. I don't yet, but I could add commonly called numbers. I could say, put customer care. That's a local call with the ISDN numbering plan. Maybe I put information. Another local call with an ISDN numbering plan. Maybe I want to put my cell phone in here. National call, ISDN numbering plan. Okay, so any commonly called numbers you can put in the phone book. If you do need to see the decoded messages, if you set up a filter in here and enable a layer 2 filter, all the keep alive messages that we talked about earlier, those receiver readies aren't going to be stored in the buffer. It only puts in the setup messages and connect messages and that kind of stuff. So it's easier to go through a capture file and look at them. So I'm going to go ahead and set up a layer 2 filter here. And those are the key things to set up on your HST. So again, in the decode screen, enabling a layer 2 filter. Pattern screen you don't have to worry about. You can do bit error rate tests on if you're calling from one test set to another. You can BERT out a B channel, but more often than not, you're just doing call plan testing with these, so it's not relevant. Under phone book, you set up your phone book. Under call, you have to specify your directory number and number to call. And most of the other stuff stays at default unless you're using a proprietary call control or you're not B8ZS, ESF. The home key will bring me back to my main screen. Now we'll take a look at this stuff on the T-BERD. So I'm going to hit the setup button here. We'll start out at interface. I'm terminating. I'm B8ZS. I'm ESF framing. I'm not going to worry about pattern because I'm not making data calls to another test set. But under ISDN, I have 3 sub-tabs to emulate an NT, to use national ISDN NI2 call control to place voice calls on any B channel. I put in a directory number here. Number to call here. For incoming calls, I'm going to prompt, so I'm going to, it's going to pop up a message saying, do you want to answer this? As opposed to just automatically accepting it or rejecting it. And I'm going to disable this last field here. This has to do with, if you enable it, you can control whether you're delivering or whether you're going to present caller IDs and stuff like that. I think it's more of a lab test. We'll typically do that for turn-up. But we'll leave that disabled. Under decode, once again, I'm going to set up a filter and a layer 2 filter to get rid of the keep alive messages. Let me clear out all the old stuff because there's already a whole bunch of keep alives in there that I'm not going to look at, and we'll come back and look at that shortly. I'll do the same thing here under results. Okay, so now we're ready to place and receive calls. Again, if I was on a real PRI, I would have put my cell phone number or another number in there, but I'm just calling T-BERT to T-BERT here for demonstration purposes. So under the Actions panel, I said I'd place a call. Under Call Control here, I'm going to answer it. So now I have a call active between the two. I could speak to the party I'm calling, ask them if my voice sounds clear and it sounds okay, ask them to talk back to me, and I know I have a good voice connection. At that point, I can disconnect the call. Likewise, I want to verify I can get incoming calls on my HST-3000. I have that party call me back, or I call back from my cell phone. I hear it ringing. I'm going to answer it. I get an indication, hey, a call came in on B1. This was the phone number that was dialed. Have them disconnect. It should come back and go to a disconnected state. So I know I can place and receive calls now. If I want to then go through my call plan, I can go speed dial and call information, make sure that call goes through. Dial the next number in my speed call plan, and just make sure that all the required numbers can complete properly. So that's how I do it for my HST. Likewise for my T-BERT, I could be placing and receiving the calls from here. In both cases, if I need to troubleshoot, I have a variety of statistics we've already looked at, but I also have D-channel decodes I can look at. So in the case of the T-BERT, there's just a regular display. Where is it at? Is it under ISDN? D-channel decodes, there it is. I'm going to enlarge the screen, but this is my setup message. It's a lot of detail here, but some of the key things are it has the calling party number in it. There's a number I called from it, has a called party number in it. Channel ID. It went from the TE to the NT. So that was an incoming call for the T-BERT, which is an NT. The next message was a call proceeding message, an alerting message indicating the phone was ringing, a connect message, and then it was acknowledged with a connect acknowledgement. So at that point, started speaking and conversing for the call. The timestamp for that was 20:03:55, and it looks like just about a second later, we disconnected the call. The cause was the user disconnected it, and it was a normal event, normal call clearing, as opposed to being a network issue or user busy or anything like that. And then it was released. So likewise, I could see those results on my HST-3000 under the results by capture and D-channel decodes and displaying them. The HST, I didn't clear everything out, so all of the there were 392 messages. Most of them would like to keep alive, and the messages just initially bring up the link at the very end. Will be the last call that was placed. Okay, the last thing I want to show you on the HST is the multiple call mode. Oops, what am I doing? Call, there we go, dual call, multiple call. Back to the home screen. There's a new display option here called Call Summary. And here, right now everything's idle, but I can go into any channel, go into Actions and dollar call. Go back to my call summary, go to another channel, place another call, or I could place call on all 23 channels at once if I wanted to. So it lets me verify I can load up all the channels with calls. The T-BERT is currently limited to a single call. If you do have T-BERTs for PRI and that's something you'd like to see, just let me know. I'm trying to build up a business case and get that put in the next release. So the more fuel for the fire I can get, the better. But that is one feature that's missing on the T-BERTs versus the HSTs. Are there any questions regarding ISD and PRI testing? Let me go to the Q&A panel and see what's in so far, and I will also, encourage you to type in any additional questions if you have them. Okay, I have a question regarding the HST-3000. I have a T1 module for the HST-3000. However, I do not have ISDN, call, etc. features. Is there a web site to download the files? ISDN PRI is an option on the HST-3000, so it's not necessarily on your units. On the T-BERTs, it's standard. If you have T1, ISDN PRI comes standard. But the only standard feature in this menu is BERT VF, which lets you do TIMS testing or send voice frequencies or listen to voice on a T1 isn't standard, nor is ISDN PRI or signaling. So if you want them, you have to purchase it. When you do, we would give you an option key to turn it on. So it's not something needed to ship in to get upgraded. It would be a field upgrade that you could do from the system menu. When you update your T-BERTs, basically, or HSTs, you just need to go into the system menu and then under Tools, Options, Revs, Copyright, you can then add new options by typing a code in here. I have another question. How do you disable auto answer on the HST-3000? Let's take a look at that now. Let me go back to ISDN PRI. We saw it on the T-BERT 5800. I don't think I pointed it out on the HST, but on the T-BERT 5800, it was in the call screen where instead of prompt, I set it to, you can set it to accept, prompt, or reject. Likewise on the HST-3000, we'll have a similar option. Just need to get back into the setup menu. I think it's going to be under ISDN. Nope, it's under call. Sorry. Actually, I don't think that's available on the HST. Let me double check here, but it is on voice over IP, what we're going to cover next. But yeah, it looks like that's not an option for the HST-3000. Oh, wait a minute. I think it is when I go back to, yeah, let me go back to dual call. I don't think it's an option for multiple call mode. When I go to dual call, call answer mode can be set to prompt, accept, or reject. Okay, I have another question about placing 23 simultaneous calls if the T-BERT won't take all 23. Yeah, you'd have to, I guess, to do this in a lab, between two pieces of JDSU test equipment, you would have to go HST-3000 to HST-3000. Out in the field, you would want to call a number that you can keep active. So I know a lot of people that will call time and temperature, or will call maybe their customer care number where they have a long recording. Because you obviously can't make 23 calls to your cell phone or another device that only accepts a single call. So you want to call into some type of an automated recorder. Okay, there's another question about when you place calls, whether you can actually listen to the conversation, and yes, you can. With the HST-3000, there's an onboard speaker and microphone, so you can speak and listen to the other party when you do it. I didn't have that set up on my equipment, but yeah, normally that's what you do. So let me go back to my slide here. There's a microphone and speaker built right into the HST. You can talk and listen. If you're doing it with a T-BERT 5800, you need to plug a headset into the headset jack. If it's a T-BERT 6000A, you also need a headset. And it actually depends on the revision of the unit, whether you use a headset jack on the MSAM itself in the side of the unit, or whether you use a headset jack in the USB port on the top. So I encourage you to contact TAC before you try to do that with the 6000A to make sure you have the right equipment, or contact me. And let's see, a couple more questions here. I guess that was timely. Somebody just had to log off because they had a PRI troubleshooting call come in. Does 5800 have option to program speed dials for out? outbound calls, just like you can on the HST-3000. There is not currently a speed dial on the T-BERT 5800 either. That's another feature that we're looking at adding in a subsequent software release. But right now it's just single call, and you have to enter the call in the setup menu here. Another thing that actually I think they've already done it just hasn't been released yet. But the next release in the quick config here, you're going to be able to change the phone number you're dialing just by clicking on it, typing it in here, and you could have a drop-down menu that's going to list like 10 most common calls that you've placed, and you'll be able to select from that drop-down menu any recently placed calls. So we're working on methods to make it easier for you to use and more efficient for you. So whenever you have ideas like that, I really encourage you to let us know the things you'd like to see in it, and how it can be adapted better to your workflows, and we'll do our best to get it worked into our roadmap. Okay, I think that's all the questions on PRI. So let's move on to voice over IP and SIP trunking. Okay, voice over IP is basically just a methodology for doing voice on IP networks. It was named pretty appropriately. There's a lot of different ways voice over IP can be implemented, though. The way the voice is sent is fairly standard. We'll look at some protocol stacks, but it typically uses a signaling or a messaging protocol called RTP, a real-time protocol, to carry voice that's been encoded using a codec. Commonly, it's 64 kilobit per second voice coming out of a G711 codec that's basically put inside the payload of packets. But there's also protocols required to set up and tear down the calls. And session initialization protocol, or SIP, is what we're going to focus on today, and that's become the most common protocol used for signaling currently. The SIP trunking, basically it's a voice over IP service based on SIP. It uses SIP for signaling, and service providers use that to deliver telephone services to a IP PBX as opposed to just an ISDN PRI PBX. A few key terms I want to go over with regards to SIP. First off, SIP trunks can be either registering or non-registering. So there's two ways they can be implemented. We'll talk about some of the messaging that takes place in order for the trunk to come up, but a registering trunk, think of it kind of like the D channel on ISDN, where messaging has to be exchanged when the link comes up before you get into a state where you can place and receive calls. So in that case, a register message comes out of the test set or the customer's PBX. It contains usernames and passwords and other information to authenticate the line, and once that takes place, then calls can be placed. But SIP trunks can be also be set up where a registration isn't required, and that's referred to as a non-registering trunk. A couple other key things in the terminology. We've already talked about billing telephone numbers. When we set up a PRI, we had to enter a billing telephone number, and that's got to be entered in the setup for voice over IP as well. It's entered as a value called an alias. So an alias on a SIP trunk is typically the billing telephone number for the PBX. For non-registering trunks, there's a value that you have to enter called a URI, or Uniform Resource Identifier. And that's used to place calls. When you place calls on a registering trunk, all you have to do is enter the phone number, because a registration message, associated with a particular IP address, and all that extra overhead is carried, is accomplished through registration. But when you place calls on non-registering trunks, you have to enter URIs, which are normally in the format of phone number at a domain or add an IP address. So maybe it'd be 321.243.0600 at 192.168.1.1. So there's a little more typing you need to do when you're configuring non-registering trunks. So you have to enter these long URIs. The devices on a SIP trunk are typically going to be a customer's PBX and a device similar to IAD, but in SIP terminology it's called a session border controller, or an SBC. And again, Cisco and Edgemark and Adtran and several network equipment manufacturers will make these devices, and they'll provide a SIP connection from that device, which is left to customer premise to the PBX, and then it'll act as kind of a proxy, so everything's sort of done locally between them and acknowledged locally, but it establishes another voice over IP and SIP connection through to the head end or central office where the communication server or gateway is that provides connectivity through to the public switch telephone network. The customer equipment is referred to as a user agent. So from the IAD or the SBC's perspective, the PBX is a user agent, or when you're doing a turn-up test, the HST-3000 or the T-BERT. From the communication server's perspective, this SBC, Session Border Controller, is the user agent. There can also be proxy servers that acknowledge things. There's also a registrar that's required for registering trunks that stores all the authentication information, like user names and passwords that allow registration to take place. So those are some of the key network elements for SIP trunking. Protocol stack is based on IP. So you have a standard IP protocol suite consisting of applications, a transport layer, TCP or UDP, IP network layer with IP addressing, and then a network access below that. The network access is most commonly Ethernet, but it could be DOCSIS or PPP for that matter. Could run over any data link. Network layer is always IP. It's called voice over IP for a reason. So network layer is IP, and then transport layer. Voice over IP actually uses both TCP and UDP for different protocols required. The three main protocols used for voice over IP are RTP, a signaling protocol. In this case, we're focusing in on SIP, and then a control plane protocol called RTCP that we're going to talk about. But RTP, or real-time protocol, is what carries the voice. So a codec is going to encode the voice into a 64 kilobit per second stream, or maybe compress it down as low as 5 kilobits per second or so, and carry that in RTP packets across a UDP transport and an IP packet. And again, SIP is the most common signaling protocol, but there's a lot of other ones out there as well. MGCP was commonly used by the MSOs and cable companies for residential voice. H.323 was the original signaling protocol, and then there's Cisco proprietary protocol called Skippy. There's a Nortel proprietary one called Unisim, and there's probably a couple other ones out there as well that I didn't list here. But again, SIP is the most common for business voice, and that's what we're going to focus on today. We'll talk about RTCP in a few minutes too. But the most important too, that RTCP might or might not be implemented, but you always have to have signaling to make the connection, and then RTP to carry the voice. The signaling goes to a call manager, whereas the voice just goes between the end devices on the voice over IP link. Now RTCP, and so that's a control plane protocol. It's optional for voice over IP, but basically it's used to get information from a far-end device on the quality of the voice. It stands for Real-Time Control Protocol. It's a QRSS monitoring protocol. So if it's turned on as RTP packets are sent, voice packets are sent from one device to another, the device receiving the packets will report back using RTCP as to whether everything's being received okay or not. If some packets are dropped, or if there's errors in them, or if there's too much jitter or other types of issues in the transmission, these error reports go back to the originating equipment to indicate the status of the quality of the link. Not all vendors implement it, and it's not turned on by default on all vendors' equipment either. But if it is turned on, then when you're placing calls with your HST-3000 or your T-BERT, we will look at these packets, and you get extra diagnostic information in order to assess the quality of it as well. They're only sent every few seconds. It doesn't take up a whole lot of bandwidth as opposed to RTP packets, which are sent at a rate of 50 packets per second typically when a voice conversation is active. Here you get one packet every 3 to 20 seconds, so it's doesn't add a whole lot of extra doesn't take up a lot of bandwidth, but it does provide a lot of value when it comes time to troubleshoot QoS issues. So that's RTCP. Let's talk a little bit more about SIP now. We went through the different messages used for ISDN PRI in the last session. We had messages like setup messages, the setup calls. We had messages like disconnect messages to tear down calls. SIP has the same types of messages, but they have different names. The message to initiate a call in SIP is called an invite message. The message to tear down a call is a bye message. The message to establish a link was a SABME message in PRI, but it's a register message in SIP. So the same types of functions take place, but we have different names for the messaging. The acknowledgments that come back also have different names. Instead of being called ACKs, like a connect ACK or a setup acknowledgement, you have messages like OK messages, which is an acknowledgement in SIP, or trying messages or decline messages. So there's different types of responses as well. A typical message exchange for registration would involve sending a register message from a user agent to a registrar. The first message that goes out would get an acknowledgement that it's unauthorized, and then a second registration message would add all the credentials, like usernames and passwords, and it would be acknowledged with an OK message. So at that point, the state would become registered. For call setup and teardown, an invite message would be sent. A ringing message would come back, and an OK message, and an acknowledgement, and then voice could be sent back and forth. At that point, you're connected. A bye message and an OK message would tear down the call. It's the same basic function as on a PRI to set up a call, to carry the voice, and to tear down the call. It's just using SIP-defined messaging instead of National ISDN-defined message names. It's using RTP instead of B channel to carry the voice. And again, SIP messages to tear it down as opposed to National ISDN or Q931. Now, since all the voice is being carried in packets, test equipment like the HST-3000 and the T-BERTs can take advantage, and they can decode the packets as opposed to just being able to put it through a codec and play back the voice. All the packets for RTP carry sequence numbers and timestamps. That allows the test equipment to be able to detect packet loss. So by looking at the sequence numbers, if there's a missing sequence number, hey, we know there's packet loss. By looking at the timestamps, we can measure jitter in real time on the voice over IP flows too. So we take advantage of those fields in the packet headers in order to give you those types of measurements. The three key things that are going to affect quality of service for voice are going to be packet loss and jitter, as well as the overall delay on the link. Packet loss is important because, you can't play back voice conversation if the packets are dropped. Now, for voice over IP, packets are typically sent 50 times per second. So every 20 milliseconds, a voice is put into a packet and transmitted, and then the next 20 milliseconds in another packet. So I just say Mississippi, 50 packets go across the link. Just the is probably 2 or 3 packets. So if a single packet gets dropped, it's pretty easy to conceal it, because the receiving equipment, the receiving codec, will just play back the prior packet 3 dB down. But if there's back-to-back packets lost, then it starts, the voice starts to get choppy and garbled, and it becomes very noticeable. But low packet loss can be concealed. For fax, it can't be concealed. For fax, you can't tolerate hardly any packet loss. But for voice, there's some tolerance there. Delay is going to be the next thing that affects voice quality, and you are going to have more delay on a voice over IP than a traditional POTS connection. But as long as it's under 150 milliseconds or so, it's not real noticeable to the user. But once it gets above that threshold or so, it's noticeable. And if it gets too high, people will overtalk each other. They'll say something. It'll take longer than they anticipate to get the answer from the far end, the party they're talking to, and they repeat themselves when their answer's coming back. Worse than that, though, it aggravates echo. So, when you have long delays, you have long echoes, and it's very detrimental. It'll bother your subscribers. So, delay is something you need to pay attention to. The other factor is jitter, which is the variance in the delay. I mentioned that the codecs generate packets every 20 milliseconds to encode a voice conversation. Codec on the other end of the link that wants to reconstruct that and play back the voice wants to pull a packet off the network every 20 milliseconds. At the start of the call, they'll typically buffer up at least one packet into a jitter buffer, and as when the next packet comes in, they're playing back the prior packet, and then they have a little bit of a buffer so that if a packet does arrive late, they still have something to play back. But if there's too much increase in delay on a particular packet, hey, the conversation has to go on. So it's going to treat it as packet loss, and when that packet arrives late, it's just dropped, and it has the same effect as if it was packet loss. So excess jitter is going to have the same effect as packet loss for voice over IP quality. So those are the 3 key things that need to be monitored to ensure that you have good quality on voice over IP networks: latency, jitter, and packet loss. There's a value that is calculated on our test equipment, and also a lot of network equipment will do it too, and it's called a MOS score, a mean opinion score. And basically it factors in latency, jitter, packet loss, the type of codec that's being used, and then a few other factors, and based on that, it grades the call. Typically, anything 4.0 and above is considered toll grade, good quality voice. Anything below 4 typically means that you need to work on the network issues in order to improve voice quality. So with all that in mind, there's 3 key areas that we want to focus in on when we're testing voice over IP. First is verifying that the link activates properly, so that you can register with a registrar. Next, proving connectivity to and beyond the signaling gateway, so you're making sure you can place calls on and off networks. And then finally, to ensure call quality. So doing that by viewing MOS scores for the active calls when you place a call. Finally, you can do your protocol decodes. Look at the signaling messages too. So you can get capture decode loaded on your T-BERDs. The HSTs have built in their own proprietary protocol analyzer too, where you could actually look at the SIP signaling messages to determine why calls aren't setting up properly or why you can't register. But those are the 3 key areas of testing. I don't have a SIP trunk, and unfortunately, you can't. The T-BERDs and the HST both only act as user agents. They don't act as registrars, and they don't act as communication servers when you set them up to emulate. So they're designed to be used at the customer site to place and receive calls, either emulating a telephone or a PBX. So I can't do a live demo, but I can demonstrate the setup to you. And I can also make available to you a job aid that's going to go through the setup. But I have job aids for PRI as well, for that matter, but also for SIP trunks. And if you contact your account manager, he can get copies of these. But let me see if that'll come up. If I'm sharing my application, hopefully this will still share with you. But I'll open it up and show this to you. But this document kind of walks through how to set up, how to, but, it's a Word document. It can be edited to make it your own, but it'll walk through how, little typical network configuration, how to set up the meter to do a given test, kind of screen snapshots to launch the test, to configure it, to place calls, to receive calls, to verify registering. So all that's in a job aid that I'll be glad to make available to y'all. But let me at least demonstrate the setup procedure to you. I can show you that on the HST as well as the T-BERT. We'll start with the HST. So I'm going to hit the cancel key to get back to the main startup screen. And the third soft key, labeled Ethernet TE, this is where you launch your voice over IP test to. It's actually a two-stage setup. First, you have to set up the HST to emulate an Ethernet device, and then you do the voice over IP stuff. So step one is Ethernet TE setup. It uses the management connector on the top of the HST to connect up, and that's actually the same connector I'm remoted into it with now, but it's showing me that that links up and that it has been sending and receiving packets on it. So I'm going to hit the configure button. I'm set up to terminate the link. Under the LAN soft key is where I set up my IP addressing. Under the ping soft key, it's not necessary to do voice over IP testing, but I can put an address in here to ping to. Normally I'd put my communication gateway or my registrar or session border controller in here, and then I can verify connectivity, verify IP connectivity to different devices before I do my test. For that matter, I could put a DNS name in that I wanted to ping as well. And I'm set up right now to ping an IP address as opposed to the name. You can do trace routes too. So I can, could put in a different address in here to do a trace route too. I'm just going to put my default gateway in, so I won't have too far to trace to. But the Ethernet TE gives you all these capabilities. But again, the important ones to set up prior to do a voice over IP test is the LAN settings and maybe the ping settings. But really, LAN's the only thing you have to set up. So I'm going to hit my home key. Oops, I hit the wrong button. I hit the configure key, and it's moving to the voice over IP setup. So let me back up here. Okay, so I'm in my Ethernet TE screen. The actions I have here are basically ping, so I can verify connectivity. Prior to doing that, I'd want to set my display to show ping results, or maybe show IP results too. Here I see my IP results. So my IP link looks good, and ping results. I can do some ping testing, make sure I have a good connection. And I don't. That's because I picked a bad address. my gateway is .0.1, not .1.1, so let me fix that. Okay, let me get back to the right screen here. Okay. So ping resolved now, I should be able to ping it. Sure enough. Okay, so now the next step, now that that's working, is going to be to set up my voice over IP connection. So I'll go into the voice over IP. I just hit the escape key and backed up. Now I'll go into voice over IP mode, and I can see it was trying to register and it timed out because I don't have a registrar on this link. But we'll go through the setup for it anyway. So there's a few different tabs associated with setting up voice over IP, starting with mode. I'm terminating. My call control standard, the SIP. My alias, as long as this is a registering trunk, that's my billing telephone number. And then I set out my outbound alias to just be dial by phone number. So then when I enter the number I want to call, I just do a phone number. So we'll go through the registering trunk process first. This is left at standard SIP, 100 reliability usage. Most equipment doesn't support that, so I set that to disabled. My next tab is audio codec. Here I specify the type of codec I'm using. Most common is G711. That'll give you a 64K stream of voice. The jitter buffer and frame intervals, you can normally leave them at default. Transmit source can be set to voice conversation or IP voice announcement. Basically, it means when, voice conversation means you're going to speak and listen through the speaker and microphone, but you can also have it just send a tone or send an announcement. Basically, it's a recording of, and it'll just play back what your IP address is and the calling number. But normally, you leave that at conversation. Leave the rest of the stuff here at defaults. If you're not doing video support, you leave that disabled. And then under proxy, if it's a registering trunk, you set your proxy mode to static. You set the IP address for your proxy or your registrar. And you enter your username and your password. QRSS, you can enter pass-fail thresholds for jitter and delay and MOS. And you can enable capture as well, packet capture. But again, the main things you need to get set up are the proxy and the general tabs. Okay, at that point, I would expect to see registration successful, after which I could enter a phone number by hitting the 1 key and hitting the OK button, and it would place the call. For incoming calls, it would just pop up a message saying an incoming call, and I'd hit the OK key to answer it. Now let's take a look at the T-BERT 5800. I'm going to select Test, Ethernet. Whether you're on a copper or an optical port, you can do both with the T-BERT 5800, or as you're testing through the copper management port on the HST-3000. but the 5800 will do any interface. But I'm going to select the copper port and voice over IP and P1 terminate. Okay. And now show me the Ethernet link came up, so I'm going to go into setup and we'll go ahead and set up the test. So I got to set up auto negotiation, whether it's can auto negotiate speed and duplex or use fixed speed and duplex. Under the Ethernet IP tab, I can set up a VLAN tag if I'm doing that, but most important, my IP addressing. So if I'm going to pull an address or if I'm going to use a static address, I would enter that here. Looks like I pulled address 0.18. And then under the VOP tab, I have a couple different setting screens here. I'm set up for SIP call control. My alias is entered here. I'm going to dial by phone number. I have a destination number. And under proxy, I'm set up to use a static address for a proxy. If I didn't have a proxy, if it's a non-registering trunk, I would change this to no proxy. And then back on the general screen here, for source alias, I would have to go phone number at IP address, semicolon, user equals phone. That's the URI you need to use for your source alias on non-registering trunks. And then for phone number, you dial by URI, and your phone number that you're calling. So you want to call customer care. It would be phone number at IP address. We will use the IP address of the SBC's LAN IP port for both of these. And proxy, you don't have to enter the IP address here. Whereas for registering trunks, the IP address, username, and password go here. But for non-registering trunks, you just go no proxy in this screen. Audio codec, once again, lets you specify your jitter buffer size and speech per frame. And transmit source, whether you're going to do a voice conversation or an IP announcement or a tone. Most of this stuff you just leave at defaults. But once that's set, then you can place calls and receive calls. You can change your number on the screen here. And once a call connects, you can go into different views to see call scores. You like MOS scores. Delay and jitter and frame loss, anything that's going to affect voice quality you can look at in the different views here. So that's voice over IP in a nutshell. Again, these job aids, we'll go through in detail the different settings and what you have to set the URIs to and everything else. So I do encourage you, if you are doing SIP trunk testing in particular, to get a copy of this. The PRI stuff's easier. It's a little more intuitive, but we'll have all that documented for you too. If you need it, just let us know. So at this point, I'm going to go back to the Q&A and chat panels and see what other questions come in, and we'll wrap this up. see, no more questions have come in. Give you all a few more minutes to ask questions, and yeah, we'll wrap things up a couple minutes early here. Where do we get the job aids again? Okay, you can either contact your account manager, so you know, whoever your main contact is for sales. You can email me as well. My information is on the front screen here down at the bottom. So here's my email address as well as my my cell phone number. So, yeah, drop me a message if you like. Now, we are recording this call. I told you that at the beginning, and that shortly, but you're going to get a follow-up email to this. It might not come out for a week or so, but you will get a follow-up email with a link to this recording and with a copy of this presentation. I'll see if I can put the job aids in that as well, where we can just give you a link where you can go to download the job aids, the PRI for the HST and the T-BERT 5800, and also SIP for those two test sets. I don't have one for the 8000. I might have them for the 6000A. I have to double check that. I might have one or the other anyway. But HST and 5800 are the two most deployed. Okay, any other questions? Okay, I'll keep the call open for a few more minutes just in case anybody does think of any other questions, but otherwise, meeting adjourned. I thank you all for your time and attention. We will have another session next Monday on Metro Ethernet testing, so if you haven't already registered with that, I encourage you to. And with that, I'll let you all sign off. Thank you.